So I've been working with Lucene for about 3.5 years now, and solar for about half that time. And today I'm going to talk about some of the challenges that we faced and the challenges that we faced and the solutions to them when deploying our search infrastructure for Bloomberg Vault. So before I get into that, a little bit of background about Bloomberg Vault. We're a hosted communications archive. So what that is different financial firms are required to keep communications data for some number of years. So they send all of that data to us. We host it we archive it in our private cloud, and then we provide search and analytics platforms and tools on top of that so that they can respond to legal requests and internal audits of the data. So the general workflow for the e-discovery use case, which is what we're covering, is a user is going to get some request from their legal department saying, we need communications that are relevant to this case that they're being sued or they're trying to find something. So it'll start with some set of users and a time range that they need all the communications. And then they're going to try and trim that data set down to something manageable. And at the end, so they're going to iterate over this query and the index, and they're trying to get the right set of results. They don't want too few results because then they can't satisfy the legal request and that'll get them in even more trouble. And they don't want to send too many results because they have to pay a lawyer to read the entire data set, and that's expensive. And also the more data you send, the more chances there are to expose something that the government didn't already know you did wrong. So there's a huge emphasis on getting the data set trimmed perfectly. So they're going to iterate over this a bunch of times, trim it down, and then there's an extraction process where we're going to package this all up and ship it to them via FTP, and then they send it off to a lawyer who reads it all, and what a fun job that must be. So to give an idea of the scale of what we're working with, we've got about 80 billion documents in our archive right now. And it's a multi-tenant thing. So we've got hundreds of different clients all sending us their data, and we need to keep it all segmented and make sure nobody gets access to anyone else's email, because that would be a big problem. On average, the documents are about 50K. So emails vary a lot in size. You'll get little meeting invites that'll be a couple K. You'll get somebody's giant PowerPoint deck that'll be a few meg. And then some nice engineer will send a 2 gig log file. And we have to index all of this because we don't know what it is, and they're legally obligated to be able to search it and retrieve it. So we have to handle this very large variance in size. There's a lot of different metadata associated with email. So you've got the senders and the participants, you've got the body, and then you've got all the metadata that goes with that. The time that it was sent, the assorted servers that it bounced through, mailing list expansion. So we have hundreds of different index fields. But our query volume relative to the data set is very, very small. So we're talking less than 10 searches per second on average over the day, which for a data set this size just isn't much. So in order to solve this, we went with a somewhat custom architecture instead of Solar Cloud. So we manage all of our shards ourselves, and they're all left offline, just cold on disk, until they're needed to serve a search. And then a search request comes in from the application into our search manager, and it goes to the shard mapping database. And what this is it holds a mapping of where all of our shards are, and then some meta information about those shards. So the customer that they're for, the data type, and some other information. So we select a subset of those that are needed to fulfill the search request, and then we send load requests to all of the Solar servers, or to a subset of the Solar servers saying, here, load up all these shards that we can run a search. And they go to our shard store and load those all up, do the cache warming, and then we send a regular distributed search to one of the Solar servers and give it the reference to all of the other shards, and it does well, that was supposed to look like it doing the distributed search. So it goes out to all the others, it gets the pieces, aggregates that together, does ranking and sorting, and gets the first page, and sends that back up. So this works pretty well. We're able to trim down. So rather than searching the entire 80 billion document corpus every time, we can trim this down. We've got a few different applications built on this. Some of them only need one shard out of the set, and some need a few hundred. But we're able to tune that so that we have to search as few things as possible each time, which is a big time saver. So one of the drawbacks that comes with this is that search requests comes in, and if you have to load hundreds, that starts to take time. It takes a couple seconds to load each of them. If you do it all, even if you do it all in parallel, you're still looking at a couple minutes. All the caches are cold, nothing's loaded. So that we had to make some improvements on that because nobody wants to wait 2 minutes for their search to come back. That's a little frustrating. So what we did is we created what we refer to as incremental search. So what this does is the search request comes in from the application as normal, but rather than sending all of the load requests out at the same time, we'll send it to the first shard, and it'll load it, and then we'll send the search request to just that one, and then we'll send up a partial set of responses, or a partial set of results. So this will be whatever data we got from the first shard, any facets that were requested, and a hit count thus far. Then, in the background, we'll send the load request for the next shard to a different Solr server and send a non-distributed search to that. And then in the search manager, we're going to aggregate the facets and hit count and results from the first shard and the second shard, and then send another response back up to the application. And then to the user, they'll just see their hit count tick over, and all of their facets update. So then we repeat this for all of the shards. And it's not actually single-threaded in practice, but it's easier to describe. So we have a thread pool that goes through these and does it somewhat parallel. But rather than blocking the user until the whole thing is done, we can provide a pseudo-streaming interface to the search results. So it'll come back into the user, and it provides a little bit more responsive and interactive user experience. And so it kind of just goes, whatever. Okay, so this still leaves the problem of this first shard load. It's still a few seconds. And users are impatient. They want to review these results so they can decide if they've entered their search criteria correctly. Do they have the right people? Do they have the right keywords? Does the hit count look like it's going to be something absurd that nobody's going to want to pay to read? Okay, so the improvement that we made upon this is what we referred to as pin shards. And so what we do is we select a subset of the total set of shards, and we say these are always going to be left online. Generally, because we're doing date range sorted searches, it's the most recent data. And then when the search request comes in, we don't have to wait for that load. We've got the caches are slightly warm if they searched it the day before. And so we can serve up that first page of results really quick, and then in the background, continue through loading all of the results, or loading all of the other shards, calculating the rest of the results. And the user, they don't notice that as much. All they care about is they got their first page and they can start browsing. And so we can get the total response time, in the best case, less than a second, but it varies a lot, but depending on the application and how complex the query is. And then a few minutes later, once we finish scanning all of the shards, they'll get their total hit count, and they can act on that. They can say, well, that's good. I like what I've got. Let's export that and move ahead with it. So because it's a multi-tenant environment, and there's a lot of different security concerns with this. So everyone's familiar with the normal access control list models. Users have access to this set of documents, or users have access to this set of documents. There's a whole bunch of different solutions out there. They all work really well. One of the interesting and somewhat unique challenges that we've run into is different users have different views of the same document. So in this example, user 1 has permission to view and read and search the red text, user 2 the green text, and then user 3 is some kind of super user. They can search and view the whole thing. So we needed to find a way so that when they entered searches for keywords that only appeared in their section of the text, we wanted the hit count and the results returned to reflect that. So there's a few different approaches that we tried. So you can post-process each document. So you run the search against the complete document, then you take it, you strip out everything that the user doesn't have permission to view, and you check to see if they still have, if it still matches their search criteria. It works. It's very computationally intensive for large result sets, and it introduces a great deal of coupling between the search backend and the application. Now the application has to send, in addition to just a Lucene query, it has to send somewhat detailed instructions about what it's trying to accomplish with this query. And we wanted to try and avoid that. We've set it up so that our backend and our application aren't tightly coupled. We provide an API, and they can search and do whatever they want. So that didn't really work so well. So the next option is you generate unique views for each document. So you take user one's red text, and you create document one underscore view one, and you shove that in the index. You take user two's view of the document, and you generate a unique subset and shove that in the index, and user three, and so on. Again, it'll work, but in our case, we had thousands of views of some of these documents. So now you take the 80 billion documents, you turn it into 80 trillion documents. You're talking about a whole different set of problems. It also gets a little confusing because now you've got weird hit counts and you have to dedupe. And it works, but again, it's not great. So the next approach that comes up is dynamic fields. So if we have a field text, and we've got our three views, 1, 2, and 3 from the previous slide. So view 1 has access to value 1. View 2 has access to value 2. View 3 has access to both. So you go ahead and you make three fields, and you just append the permissions to the field itself. And we tried this, and it works, again, as long as the number of views is manageable. And what we found is that because of the way these permissions are done, we ended up with hundreds of thousands. So a given document will have a few thousand views, but then over the whole data set, you've got hundreds of thousands of these. So now you have an index with hundreds of thousands of different fields, some of which only exist in one document. So the first thing that you run into is to improve performance. The strings are all interned for the field names, and in older versions of Java, that memory is somewhat limited. So you'll bounce into that. You can raise that and get past that. It bloats the index out quite a bit, so now you've got a lot of duplicated fields. You've got a lot of fields that only occur in one document, so you've got weird relevancy things that go on. It works up to a point, and it actually works really well up to that point, and then it fails catastrophically with indices that grow out of control in terms of the size and the complexity. So what we finally settled on was we instead of encoding the permissions in the field name, we encode it in the tokens on the value side of it. So what we do, we run the regular tokenization, and then we take each token for the different sections and prepend the permission. So it doesn't exactly look like this, but close enough. So you'll have view 1 underscore value 1. View 2 underscore value 2, and then all you have to do is pre-process the query a little bit to take the tokens the user's searching for, prepend all of their permissions, and run it through. And this is what Solr is really good at. It likes big blocks of text, nice manageable tokens, and so the end result, the application and the backend don't have to agree on much other than here's how the permissioning system is going to work, and here's how the tokens are going to be generated. It's a pretty simple little library to publish that out. And then they can generate normal Lucene queries, do phrase searches, all of the things that everyone loves, and it works really, really well. So overall, kind of went through some of the scalability stuff that we've taken, some of the approaches we took there, and some of the unique security stuff. So I'll open it up for questions. Yep. So what was that? How many of these can we add? Yeah. So the question is, what happens when we have lots of different views? I understand. So what happens is we just end up with lots of tokens. And so if a user has a lot of permissions, we end up with big query strings. We're sometimes dealing in megs of like Lucene query text into this. So I mean, it expands, but Lucene handles it fine.
So yeah.
Did that answer it?
So basically, it's I'm assuming that the view one is like a group type of things about the user one belongs to certain group, and then the view one assume that it's a group style. So that means like you add all the groups to all the groups details in the value itself. That's
Yep.
what it looks like. Okay. So sorry, one more question. So when you do the incremental search, so actually you are you send the request to the first shard, and then like you return the result, and then show in the user, right, for the right. So when you so actually you are showing the faceting there also, right? So what happens? How do you update the faceting when you hit the second one? So basically, you manually update the faceting details and then show it in the user for the user.
Yeah. So we've got code that will take the facets from the first response and the facet from the second one and just merge those together, and then send that back as another response to the application, and then it just refreshes the page.
So your application does the faceting incremental instead of Solar doing that?
Well, so we get the facets from each shard, and then we merge them together.
Oh, okay. Okay, thanks.
Yep.
Balancing your shards, so the number of documents coming in, I'm curious what strategies did you have to come up with to properly fill them, and how did you deal with unbalancing?
So right now they're pretty unbalanced. We chunk them on some pretty static rules because that makes the indexing pipeline a little bit more stable. But we've just, through trial and error, we found a size that kind of serves as the maximum where the load process is quick enough. And we say, well, we'll let them go up to that big. And then we've got a whole bunch of them with a very long tail of, increasingly small ones, including some really degenerate cases of single document shards.
Why did you decide not to use Solar Cloud?
So the big thing is that we need to be able to take them offline, the shards offline to free up the memory. The question was why didn't we use Solar Cloud? We didn't use it, so we wanted to be able to take everything offline so that we can run this on less hardware. With Solar Cloud, it's kind of implied that your whole data set is online and searchable all the time. With our use case, so we've got a few hundred different clients. On any given day, less than 10 of them will actually do anything. So there's no reason to have all that stuff sitting in memory and ready to search if no one's going to use it.
Are you trying to keep the shards per client, or is that like data is mixed in all those shards?
So the question is, do we keep them per client? Yeah, so the shards are all separated by client in addition to other criteria. Yeah.
I wonder, did you try to use payloads for these security markups for these?
Did you try to use payloads to manage these security tokens?
We didn't, no.
Okay.
I'm not even familiar with payloads, so.
Okay, it's just particularly that featured for dealing with something like attaching the additional information for posting.
Okay.
For term occurrence in the particular document.
Okay. I'll take a look at that.
Okay.
Yep.
What were the total number of shards that you actually used for the whole data set?
I'm not supposed to say the exact number, but it's in the hundreds of thousands of shards.
And another question is, what kind of RAM did you use for those boxes?
Like in total, how much?
No, each box, or do you have different sizes for each?
It's a homogeneous set of machines.
Okay. So any approximate range of RAM?
They're not big machines.
Okay.
They're average-ish, I guess.
Okay, thank you.
So I work in the same team. So I think for us the problem is trying to solve this. If you can solve this problem if you have unlimited budget, right? If we were to put all these shards online and it would take so many machines, we would be out of business. So our goal was to do it in as few a number of machines as possible. So a lot of efficiencies, a lot of optimizations that we have done is to take care of that use case. So these are tiny machines. We have a few hundred, which is small for the use case, the amount of data that we have. But that was to get our salaries, essentially.
If you have any change in the security rule or you are adding a new view or something, you will need to reindex that specific shard again, right?
So in this particular case, the use case for this views thing is actually the blind copy on email, which it turns out people use a lot of. So the view is actually has to do with the interactions in the email itself. So the permissions for the document will never change. It's just the permission of the user searching it, if that makes sense. Yep.
Yeah, you have showed really a clever idea that you build an artificial field with all the content and with all the tokens. But then when you return the document to the user, what do you return? I mean, each user can just see a limited part of the field, and so you filtered. What is the response to the user?
So the question is about, for the security thing, what do we return to the user? So in the application, they've got code that says if the user's permissions are this, filter out all of the data they're not allowed to see. As kind of we send the response from the search backend with all of the data, and then we trust the application to filter that all out before it gets to the user.
Yes, you filter so the artificial field, but what about all the characters like the punctuation that probably you have removed all the punctuation from the field that you have stored, and so when you return to the user this field, and you couldn't rebuild the original field.
So the original text is actually stored in a separate field, so that we can render it without all the extra mangling. Yep. The query will include the permissions as part of the query. So the result set will only be the documents that match what they had permission to search, but the data returned, the application then has to filter that out. And eventually we're going to move that into the back end. Again, it's just a matter of making sure that we don't too tightly couple the two pieces so that we can develop them somewhat independently.
Do you see any impact on lucid scoring because of all those padded to the actual text?
So the question's about scoring. For the most part, we don't really do any relevancy ranking, since people are generally, our users are generally interested in the whole data set, not everything is relevant, because some lawyer has come down and said, here are some very, very specific criteria. So they're generally just browsing to make, the people running the searches aren't the lawyers. It's some person from their IT department that has been tasked with this. So all they've got is a set of requirements written in lawyer, and they have to convert that into, enter in the requirements, and then make sure that what they got matched so that they can send it back. So as a general rule, the requests will be a date range and a set of participants at a high level, and then they'll refine them with keywords. So a lot of these legal cases will be like, we think that this trader or this group of traders did, insider trading or something like that. So they're going to want to get all of the emails for that person, and then they'll maybe filter it, and they'll try to look for keywords related to the company that they're accused of, the stock that they're accused of trading, or maybe the people they're checking if they talk to. A lot of interaction type stuff. Yep.
I don't know the extent of use case and the amount of changes in the data, but what are some of the reindexing strategies you guys use?
So the question's about our reindexing. We have a batch process outside of this. So we don't use Hadoop, but it's conceptually very similar to a MapReduce setup where we scan all of the input data, build new indices, and then we just publish them effectively to our shard mapping database and say, here's this new shard, and then we take the old one out of the database, and that effectively deletes it from the query set. Yep. So mostly it's handled at the application level. So the back end trusts, for better or for worse, the applications to say this user has permission for this client, and then only request data from that client. But there's a great deal of security stuff there with saying, you know, this IP address belongs to this client, and, you know, login credentials and all of that. Normal. Separate shards per client, and then we actually tag each document. In case the indexing screws up, we tag there's a field in the document with the customer ID, and that's always included in the query, so that even if we do screw up at some level, it won't make it out and burn us. Yep.
Do you allow your users to sort? And if you do, how do you do incremental search?
Sorting doesn't. So sorting for incremental search either works time ascending or descending. If they want anything else, generally we make them do an incremental search first and then sort. And so then the sort goes back to the regular bulk update. But by that time, all the queries are cached, so it's quick.
And the time ascending that based each shard.
It's just a matter of which direction you traverse the shards. Mm-hmm.
So this would, I guess, probably work with only exact search and not applying any kind of analyzer or
Yeah, it'll only work with exact search or phrase search. Yeah, like queries are going to fail pretty catastrophically on something like that. Like the incoming data is corrupt? Yeah. Okay, so the question's about, it's 11 o'clock. So I'll answer that one quick. So for data corruption, email's a very loose standard. So we're just continuously improving our parsers to handle things that are less and less well-formed. Only a couple times, and it was Solar not handling some hardware failures in the most graceful fashion. But it detected them. We detected them through other means pretty quick. So.